Welcome to the Mu Analysis video on failure mechanisms in LEDs. Mu Analysis is an electronic materials laboratory. We have performed an extensive analysis on numerous LEDs. There are three ways that LEDs can fail: no light, intermittent light, and the gradual dimming of the light over time. Although failure modes in LEDs are simple, failure mechanisms are more complex. There are many mechanisms that can cause LEDs to fail. We will show examples of these. Although power supply issues can cause LEDs to fail, we are only dealing with the LEDs mounted on a product. In LEDs, anode bond wires are more likely to fail. Although both wires carry the same current, the anode wires are hotter because they are closer to the multiple quantum well, which is where the voltage drop occurs and heat is generated. This is a low-cost LED. The red arrow indicates its location. This example uses wedge bonds. When a wedge bond fails, it usually occurs at the heel, shown by the yellow arrow, as this is the weakest point. Wedge bond failures are sometimes difficult to see when looking from on top, as this image shows. This wedge bond failure actually occurred under the wedge bond. The next slide will show it in cross-section. These cross-section photos were taken of the wedge bond failure throughout a polishing sequence. Now we are able to see where the wire bond has lifted and is making intermittent contact in only a few places. This is a SEM image of a cross-section of a GaN on silicon carbide flip chip LED. The blue arrow indicates the direction of the light being emitted from the GaN. The red arrow indicates where many solder voids have formed. Current crowding has caused these voids to occur in the solder. The voiding will lead to intermittent contact and eventually open circuit. These are X-rays of power LEDs. The circles are heat spreader pads. Lack of solder coverage inside the circles can lead to overheating. On the left, the part has a bad solder coverage, yet this part has not yet failed. The failed part on the right heated to the point that the solder melted and resolidified. These are two examples of failed parts due to contamination. The left bond wire is completely severed. The right is partially separated. Compound semiconductor devices typically use gold bond pads and gold bond wires. If the gold bond pad is contaminated, failures like this will occur. The image on the right is a side view of the image on the left. The LED is on a silver epoxy die attach. The red arrow shows where the die attach has crept to the surface and created a short. In this case, the silver epoxy is the contaminant. Here we see an image of delamination in a through-hole LED. A SEM image shows a complete separation of the die attach from the bottom electrode shown by the green arrow. Here is another type of delamination. The SEM images show that unlike the previous slide, the die attach has remained adhered to the substrate. However, the blue arrow shows us a void where the die itself has lifted away. The left side is also lifting away. The purple arrow shows us a void where the acrylic encapsulation above it is pushing away. Here is another delamination example. In the top view, we cannot see the delamination. In the tilted view, edge delamination of the encapsulant from the substrate becomes obvious. These four optical images are of the failed LED on the left from the previous slide. In manufacturing, a clear adhesive was used to attach the blue and green LED dice to the package. Silver epoxy was used to attach the red die. Delamination was observed around the green and blue dice as shown by the red arrows, but the red die shows no delamination. In cross-section analysis, we observed that the clear adhesive was still attached to the dice, but had separated from the package. This separation has led to overheating and failure. This is another delaminated LED. This is an index matched part. Finding delamination can be very difficult. The telltale signature in this image is the color fringes as shown by the red arrow. There are very subtle color fringes visible on the image of the underside of this through-hole LED. Sometimes the die itself can be bad. Here we have two cross sections of blue LEDs. On the left is a SEM image showing a V-pit as indicated by the red arrow. On the right is a TEM close-up image of a V-pit. A V-pit is a relaxation of a crystal dislocation reaching down to the active zone. It does not cause immediate failure, but it can accelerate degradation by enabling contaminants to reach the active region. Let's look at dielectric breakdown. Here is a flip chip LED. The via on the left image is circled in red. The via is shown at a higher magnification in the center image. The three breakdown regions correspond to the arrows in the SEM image of the cross section on the right hand side. The SEM image shows us that the breakdowns occur at corners. This is an example of normal aging of an LED. In the right image, the phosphor has been removed. The electrode is hotter where the die is located. The phosphor has darkened more over the hot side of the package. The previous slide shows that a gradual darkening over time of the silicone in LEDs is to be expected. However, in this image, we see a premature darkening in D9 and D21. This premature darkening was traced to these LEDs coming from a bad reel during assembly. The image on the left is a good part. The image on the right has damaged vias. ESD damage at vias results in leakage current. The leakage current creates resistive losses which make the die hotter, which in turn darkens the phosphor. This LED was not heat sinked properly because an improper heat sink material was used. This caused the LED to overheat, which resulted in the darkening of the silicone and decomposition of the silicone, which then became corrosive and attacked the metallization. This is an additional flaw in the same design. This LED was overdriven. Overdriving carbonized the inner lens above the LED, which shorted the package. No metal corrosion is observed here. Remember this image from earlier? We used this example to talk about delamination. Delamination led to the failure, but was not the root cause. The manufacturer of this LED chose ENIG as the electrode plating. This was a bad choice. The LED adhesive was unable to adhere to the gold surface. Silver plating is more commonly used and is a better choice for electrode plating. Mu Analysis is offering a half-day course on LED technology to groups of 5 or more. If you would like to take advantage of this course, please contact us. Mu Analysis services enable manufacturers to reduce design time, reduce returns, and maximize product yields. Thanks for watching.